Hello. Um, Welcome to uh, yet another sample problem solving for relative acceleration. You're using a relative acceleration to analyze the motion of a rigid object. After I did this one, I realized this is going to be a clown-sized yo-yo. So the idea is you have a yo-yo or you have a wheel with two radii, and then you have a rope that's wound around the smaller one. And the contact point here is going to be point A, and we have this point here up on the very top of the wheel. And what we know is that the two radii, I'll call them RA, is going to be 0.5 feet, and RB is going to be 0.75 feet. So I should have chosen smaller numbers, then we would have had maybe a more plausible scenario, but it's okay. As far as the mechanics of it are the same. All right, and the goal is to find the acceleration at point B, given that point G falls straight down. Okay, so point G is going to fall straight down like a yo-yo would. The center of the yo-yo just goes straight down, even though the string is attached to the side. We assume that at point A, no slipping. We use this condition a lot. It's your friend. It helps us. All right. So this is what we have to do. So the first thing, a couple of observations. You know, if you tip your head sideways, then say 90 degrees, then this problem actually is really no different than some of the problems where we had a wheel rolling with gear teeth rolling along a fixed surface. And so that means we can use a lot of those results to help us with this one. In particular, we know that the velocity at A must be 0. We know, because it's just like when you had an object rolling without slipping, that the acceleration at A tangent must be 0. And furthermore, the acceleration at A in the normal or radial direction must be omega squared times RA, and it has to point towards the center of the circle, which would be in the positive x direction. Those are the results we had when an object rolls without slipping, and we worked it out when things were level to the ground. But I mean, if you tip your head, this is the same problem. So that's going to help us, the fact that we only have one acceleration component at the point of contact. Okay, so we can go through. The other thing that we know about point B, I'll change color so it's clear, is that at point B, you know, point B it's undergoing, this point would undergo circular motion, or sorry, a general motion. So you should expect in general that there is both a tangential acceleration and also some sort of a centripetal radial acceleration. So the full answer that we get will lie along the diagonal here. So we're expecting an acceleration which has positive x and negative y components. So just sometimes it's good to kind of know where you're headed so we can assess how we did when we finally arrive at the end. That's fine. Okay, one other little thing. Okay, so let's plan our route. Let's plan. We want to evaluate the acceleration. So let's write out our formula. Acceleration of A, or of B, is the acceleration of A plus the relative acceleration, which is going to be plus alpha cross R relative to A minus omega squared RBA. Now, alpha is given to us, so that's easy. R, so put that in green light special. R we don't quite have, but we've got enough. We can work it out from the links they give us. So I'll go ahead and put that in green. That's just going to be a baby step for us. And then stuff that we have to do a little bit of work to find would be omega. And then notice once I find omega, I know the acceleration for A. So once I find omega, that's done. So the task is going to be to find omega and really just plug in and evaluate. So how will we get omega? We'll find omega from an instantaneous center of motion analysis. And then once we have that, we will use it to find the acceleration at point B and just evaluate both components. Okay, so that's the plan. That's what we're going to do. All right, instantaneous center of motion. Well, I know that I have the rope. I know that it goes down. There's no slipping here. So this point has zero velocity. This is the, so point A is the instantaneous center, which means that I can say that all points on the wheel rotate with a common angular velocity about this point. So in particular, I can say, let's see, what else can I say? Oh, I don't even have to, I apologize. I'm getting my examples confused. I don't even have to work this hard. Well, I don't have to work this hard. Well, I forgot that the problem already gave me omega, so I didn't have to find it. So I don't have to find that. I really just have to start plugging things in. Okay, so let's do that. So this is done. It's in the problem. They're done. I just have to plug in and get what I get. So let's just erase all this. And I know the acceleration at B would equal the acceleration at A plus alpha cross R B A minus omega squared AB, or well, it's of the object, the wheel, times RBA. Now I can just start putting in things that I know. This equals, well, that should equal omega squared RA x hat. Alpha is in the z direction, and R AB. Oh, I need to find that here. So let's go over to the side and find that. Here's my wheel. Here's my smaller wheel. Here's the center. Point A is here, and point B is here. So I know that the vector from A to B equals, well, it's going to be RB y hat plus RA x hat. And if I work out alpha vector cross RBA, that's going to be alpha times, I have z hat cross y hat, that's just going to be positive x hat. And then I have z hat cross x hat. Oh, I apologize. I've got that backwards. Z hat cross y hat was negative, so I missed a minus sign here. And then I get plus RA times y hat. All right. So I plug all that in here, and I'm going to get minus alpha RB x hat plus alpha RA y hat minus omega squared times RB y hat plus RA x hat. Rearranging that, I get x hat times, and I have omega squared RA minus omega squared RA. Those cancel. And I have this term only in the x direction. And in the y direction, I have both of these two terms. Oh, sorry. Okay. Let's plug in my numbers here. So hopefully I didn't miss a minus sign. I may have to go back if I did. I have x hat, and then let's look at my numbers. Alpha equaled 4, and RB was 0.75. So this is going to be 4 times 4/3. So that's just going to be 3. Feet per second squared plus y hat times, okay, so that's going to be alpha times RA, that's going to be 0.75 times 0.5 minus point, yeah, minus, I take it back. Helps if you look at the actual numbers in the problem. The alpha was equal to 4 times 0.5, and that minus 0.75 times omega squared. Omega was 3, so omega squared would be 9. And if I type that in, 4 times 0.5, 0.5 minus 0.75 times 9. And, oh dear, I made a mistake because alpha was negative 4. So minus 0.4 minus 4 times 0.5 minus 0.75 times 9. This is a 9, not an A. It was omega squared, and omega was 3. And let's try that again. There you go. This gives me negative 8.75. It'd be feet per second squared. So I get the acceleration at point B to be 3x hat minus 8.75 y hat feet per second squared. If you use the Pythagorean theorem, you find that the magnitude of the acceleration is 8.92 feet per second squared, and the angle associated with it is negative 71.1 degrees. Whew. Sorry about that. Filling out numbers. Right, so let's reflect on it. We see that there is a component to the in the x direction, and then a negative component in the y direction. If you go back to our diagram, I promised that there would be a positive x component and a negative y component to find the final, or the total acceleration. All right, so that is a yo-yo type problem. I think I'll have one more example if I have enough energy for you guys. Okay, good luck.